So this is the second part of building dApps with the user-defined token on CKB. And today we're going to be going over a couple things. It's going to be a little bit shorter than last time. So first, we're going to add another operation to our implementation of the simple user-defined token. We're going to look at adding a different type of monetary policy. So we're going to change some of the fundamental logic and see how we go about changing that. Then we're going to actually do a little bit of security work and determine if our token is forgery resistant and ensure that it is, basically. And so let's just go over some of the most important concepts from yesterday. And of course, that is the biggest one is that it all comes down to one thing: building correct transactions. And what that looks like usually, what building correct transactions entails, is that generators gather pieces of state from the chain, they gather cells, they package them into transactions and send them to the network, and then verification scripts unpackage these transactions into their components and verify each of them. Where we left off with our functionality is that we have one operation really, which is issue/mint. We can think of them as, and issuance can be thought of as the first time minting, and minting can be thought of as subsequent issuance, right? So we combine them, and then we have those two queries. And if we want to add a new property, then, or sorry, a new operation, then remember where we're at with our modeling step. This workflow of modeling and development running in parallel informs the way that we approach development of new features. So if we want to add a new operation, then we start again at that first step, define the operations and queries, and then define the generator function. And the operation that we're adding is transfer. That's a pretty fundamental operation. It's hard to use a token unless it's a very special type that you can't transfer. And because our property, under our properties, we do mention that we want a token that's transferable. So it makes sense to implement the transfer function here. Now, usually we would go to the design data structures step after we have our operation defined. But since there's no new operations that we need to, since there's no new data structures that are required to implement this, we don't need to go through that step. And the reason that we know that there's no new data structures is because we didn't define any. All we need to do is make sure that the data structure we already defined of the UDT cell goes from one person to another. And just like before in the code, you see that I have this transfer method here alongside the issue UDT, the gather, and the get balance. I have this transfer method here so I've added it to my generator code as well, according to this step, define the generator function. Okay, so I don't need to model the data structures, so I can go right to the transaction design and then building out the transaction generation and transaction verification in my generator and verifier respectively. And this style of transfer is going to be very simple. And it's just that there's a UDT cell as input, another UDT cell as output. And just like with cell transfer, the lock of the input is the sender's lock and the output is the recipient lock. And this isn't only just like cell transfer, it basically is cell capacity transfer as well. So in this naive scheme, what's happening is that not only is the token amount, which is stored in the data field of the cells, not only is that transferred, but so is the cell's capacity that's storing the token amount. Now, there are maybe other ways that can be done, and actually there are other ways that can be done that have been specified, and that will be stuff that's in the code project, but beyond the scope of the simplicity of this presentation. So right now we're just going to use the simple transfer here. And the constraint is that a transfer should not be minting, right? Because minting has special permissions. And so the constraint here is just that the UDT amount in the output cannot be greater than the UDT amount in the input. So these tokens can be transferred, but new tokens cannot be created in the process, cannot be minted in the process. And since I'm at this step and I have my model of what the transaction should look like, the next step is to, of course, the developer step, which is the construction of the transaction and the verification of the transaction. We went over yesterday how this basic generator workflow is what you need to do for pretty much any operation. And so let me show you quickly the transfer method. The transfer method looks very similar to the issuance method. One change is that inside of the amount function, inside the transfer function, it takes an amount, and the amount is what's created during the first part of building your data, building the output. And the lock of the output is the recipient lock, but it's still, apart from those minor changes, this is pretty much the same, which is building your outputs, gathering your inputs and packaging them into a transaction, signing the transaction, and sending the transaction. Now, you can see that if you, maybe some keen people might see that, what if the amount that you put in here, you don't actually own that much? Well, ideally, a generator code would not want to submit a transaction that they can so easily verify is incorrect. So a more sophisticated and better method here would check if the sender actually has enough UDT to satisfy the output amount. And it would do that by gathering up all the UDT and summing that up and determining if that's possible. But for the demonstration purposes, this is sufficient. Okay, so that's pretty much it for the generator code. It's just building the outputs and then packaging everything up. The verifier code here, it's if the generator code gathers a bunch of cells and packages them up, the verifier code is going to basically deconstruct the transaction, load in cells, load in UDT cells one by one, and check if they're valid or not according to some rules. And these are the specific rules here, is checking the amount in the inputs and checking the amount in the outputs. Now, loading in cells that have the same script hash is quite easy because, and it's kind of an optimization in the transaction process on CKB, is that if you have two cells with the same type field, which means that their type hash field, with the hash of their type field is the same, then that script that's included in multiple cells in the transaction is still only going to execute once. so that script has to ensure that it's checking all of the inputs and outputs that have that script hash, right? And that's pretty easy to do here, and I'll show you. So adding up the inputs and the outputs in this particular, inside the verifier in the scripts, comes from the verify UDT usage method. And as you can see here, I'm setting the input amount to 0. I'm loading in the raw data, following that same pattern, loading in the raw data, turn it into molecule, use molecule to do some sort of access or validation, and then just adding the input to the current amount. And you can see here that there's this variable called CKB source group input. And that allows me to only load cells from the input in which the type hash of that cell is the same, are the same. So basically, it's loading in inputs where this particular script is executing against them. And so every cell returned by this is going to be a cell from the inputs field that has this particular script. And I do the same for outputs in another loop here with CKB source group output instead of input. So this only gets loaded, this only gets executed. The entire script only gets executed once for all of the different cells in that transaction. Okay. And that's pretty much all you need for verifying transfer method. And I'm going to move on to new monetary policy and talk about, okay, how do we think about where to add new logic, and then how do we go about doing that? Because there are actually multiple options for where to add new logic, and some of them, and based on what kind of logic you're trying to add, one place might make more sense than another. So we know that we have the governance log, which we talked about before, as the logic that contains governance logic and is referenced in certain types of transactions, right? Then we have the UDT definition, which contains the core business logic. That's the script I was just showing you, and that is attached to every UDT cell. So where do we add these different our new custom logic in one of these, or maybe we change the design and add into a new script entirely. Right? And this is kind of a rule of thumb on where to place custom functionality based on the type of logic you're trying to add. So token invariants, or rules about tokens that should hold in absolutely all situations, should be included in the first option, this UDT definition cell. That's because this code hash is always going to point to this code, and so by adding it here, you're ensuring that it's always being executed against transactions involving UDT cells. And that's because even though this governance log hash is included as an ARG, remember that not everyone can unlock an input blocked by the governance log. And this is kind of a way to implement conditional logic to enable things like minting. Right? So invariants, rules that should always hold, should be added into the UDT definition code. We also have maybe default logic. So this should also be added into user-defined token definition code cell. And default logic is basically the logic that applies to people, to users who don't have any sort of additional permissions based on governance, right? So in our minting operation, we use a governance lock to signal to the TypeScript, to the UDT definition code or the TypeScript that that the signer of the transaction is authorized to do something that other users aren't allowed to do. And so certain default logic becomes overridden, and that default logic is the basically some verification, or making sure that the amount of UDT in the output is not greater than the amount in the input. So that type of logic also you can add in the UDT definition. And additional governance rules, now that can be added into the governance log script, because these governance rules can also be thought of as conditional rules, and we're going to see, or rules only applied in certain circumstances under certain conditions. We're going to see that in a little bit more depth here, is that since these rules are only applied to certain types of users, these governance rules, they are an example of conditionally delegating part of verification onto a different script, which is a more generic pattern that we're going to look at right now. And if you see here, this on the right, there's this basically just an if else statement, where if the transaction has some property, then this TypeScript, this hypothetical TypeScript, will apply rule 1, whatever rule 1 is, right? Otherwise, if it has a different property, it's going to apply rule 1 and it's going to apply rule 2. So based on the TypeScript, looking at the properties of a transaction, looking at the various components of it for specific patterns, it can apply different rules. So in other words, the TypeScript can conditionally apply rules if the TypeScript knows what patterns to look for in the first place. And it can look in many places. It can look and get certain info about the block, not a lot, but certain info, block headers. And it can look inside inputs and outputs, transaction dependencies, witnesses, including the witness args, right? And then since it can look inside inputs and outputs, it can look inside cell data as well, of course, and look at its own scripts, other cell scripts, and the args being passed to those scripts. Now, in minting specifically, which is the example of this in our simple UDT, we have two places being analyzed for a specific pattern. That's the inputs and the script arguments. So you see here is that we have to check if the admin mode is enabled somehow. And if the admin mode is enabled in our UDT, based on our UDT definition, then our script allows minting, right? So we have to determine what admin mode means. And the way we do that is that we search for an input with a specific log hash. We load in the admin script dash from our args, and so we have both. So we're looking in both places and comparing one against the other. And in that way, we have all the information we need to make the decision about if admin mode should be enabled or not. And essentially, the function of this is that the governance log script here, which is the hash of which is the admin script hash here in this example, that acts as a signal to this UDT definition code to override certain default logic, i.e. this logic right here, where the UDT input amount that's actually, that equivalent sign should be reversed, but where we're comparing the two. So the governance lock is a signal to this script to override certain logic. And so in this way, if the UDT definition is signaled that certain logic should be overridden, then it essentially delegates to the governance lock to continue with verification. It stops verifying and applying certain rules to the transaction, and the governance lock script is now responsible for verifying whatever rules it needs to. So remember, we're talking here about some sort of new minting policy. And this minting policy is going to be one that rewards stakeholders. So the goal here is to reward loyal stakeholders. And so we're actually separating the issuance and the mint operations, because only the creator can initially issue tokens, but we want holders to be able to mint a certain amount for themselves, thereby rewarding them for being loyal, right? This is just a hypothetical monetary policy. And if we think about where to add our logic, basically what we're doing here is we're modifying the permissions. We're saying that now it's not just some owner of a certain cell that can mint. Rather, anyone who owns a certain amount of UDT can mint another certain amount. And maybe we add constraints in about the amount of time you should be holding your UDT before you can mint, to enable long-term holding, for example, to incentivize that. And I'm gonna skip that slide. So in our previous mint design, we have the inputs and the outputs, where the input is one that is signed by the governance lock. One where the input is unlocked by the governance lock script, and the output is a new tokens, right? And that was our previous design from yesterday. And the new design, what we want is one of the inputs must already be one of the token cells, right? So they already have to, someone who's minting already has to own the token. And of course, we still place the lock in there, the governance lock in there, so that people can signal to the UDT definition that certain logic about some verification can be overridden. And we can apply random constraints to this here about maybe there's a cap to how much the person can mint based on how much they own. So there's a relationship between those two. And maybe we can also say that they must be holding that token for a certain amount of time before they can mint. So you can't just buy tokens and immediately mint them. You have to hold them for, say, a month or a year before you can start minting. And you can only mint once in that interval, right? So all those types of rules can be applied. And the way to do that is probably more sophisticated than the other stuff, and probably more sophisticated so that it might not make the most sense to go through it here. But you'll see in the project directory that I'll link to, you'll see an example of this, and it's heavily commented to explain. It's probably better use of that time. Okay, so like I said, we're skipping the implementation step for now of that modified mint, but we did design it. And so now that we have a new monetary policy, we have a token that's able to transfer. The final portion of this is, let's think about if our token can be forged in the first place. Remember that the token ID is the type hash of the UDT cell. And the token ID is what's used to differentiate one token from another. So if I create a token and it's compliant, it has all this data, and therefore it has a token ID of a certain type, what I want to avoid is anyone in this call, being able to create new UDT with some amount, but has the same token ID, because that would be forgery, right? You're not authorized to perform that operation. And the way that the logic that checks if a token is being minted works is that in the output, so in the output, which is a UDT cell that has this governance log hash, looks for an argument. Looks for an input in which the log hash of that input matches this argument. Okay, so if you were a thief or you're con man, you're trying to forge and mint tokens without authorization, your goal would be to create a new output with the same type hash, but the governance logic is different. So you'd have the same code hash for the type field, the same UDT definition, but this hash here, this governance script hash, would also be the same, but the logic implemented in this governance log cell, the actual logic, the executable binary, will be different, even though these two things are the same. And we're just going to zoom in on this input right now and see how this could be possible. So we're zooming in on the input, and we're looking at how it looks into the type hash. Yeah, so if we have a hash type of type, because every script field, so the locks fields and the type fields, also have a third value that we haven't really talked about yet, and that's the hash type. And the hash type can be either of hash type or of hash type of data. And so we're going to explore both possibilities here. So if the hash type is type, then this code hash is actually the hash of this field of the dependency cell. Okay. And basically, what a thief can do here is change this executable binary, but reuse the type hash. So remember, this code hash references the type field of this cell, but what gets executed is this binary data. Whoops. What gets executed is this binary data. And so you can change this, but that doesn't affect the code hash. And you can reuse the same args. So that doesn't affect the execution, because all you need to do is write executable logic that passes when the same arg is used, right? And so it's very easy to forge a token in this way. Now, one solution is to use a hash type of data. To use a hash type of data, then this references the hash of the executable code itself. If you change the executable code, then you change the data entirely. Then you change the code hash entirely. Because if hash type is of data, then this refers to this instead of the type field. Of course, if you're coupling together the code hash and the governance log, the new governance logic will change the code hash. And by doing so, the type ID the token ID gets changed. And so you can't you can't upgrade this without changing the cell. It's the token itself into a new token. So it wouldn't be upgrading a token of the same type. It'd be creating a new token with a new type entirely. So referencing a code cell by data hash essentially couples together the data in the executable code with the hash at a single point in time forever, right? And so if you want to upgrade that data or that executable code, you're upgrading the code hash as well. There's another way to do this though, and that's when we still use a hash type of type, referencing another dependency cell by its type hash. But this time, the type hash of this cell that we're referencing has a special typescript called the type ID. And the type ID we'll go into in the next slide. We'll talk about a little more, but what you need to know as a builder, the purpose and the use of the type ID is that this argument here, this type ID arg passed to the type ID code hash, is universally unique across the blockchain. You can never reuse this type ID arg. Every time you create a new cell with the code hash as the type ID code hash, basically applying the type ID script as the typescript to this cell, every time you do that, you need a new argument here that's always unique. And so if a thief tries to reuse the same code hash, they can do that. That's perfectly fine. They'll reuse the type ID code hash, but they're only going to be able to use a different type ID because the logic inside of this type ID prevents them from using this a type ID that was already used before. And we're wondering, basically, how does type ID accomplish this when there's no say index on all of the IDs? So how do we know if one's been used or not? And basically what we have to do is think about what's one thing that can only ever be used once by default, otherwise the transaction will fail. And that's an input, can only be spent once. Since CKB is more similar to UTXO style blockchain than account one, these inputs can only be used once. When you include a cell as input to a transaction, that input is no longer usable. You create a new output instead. And inputs, their actual format, so not like thinking about the fact that they are cells, but what do they actually look like in the beginning of a transaction before, say, all of this data is resolved? They look like this, they have a previous output that points to a previous transaction and the index in the outputs at which the cell we're trying to include exists. So if we wanted to include this cell, this output, as an input to a previous transaction, it would be whatever the hash of this transaction is would go in here, and index 0 would go in here because we only have one output, right? So it would be index 0. And that would be the way to include this output in a different transaction as an input. So if we can get the hash of these two pieces of information, then that's the first step to making sure that the ID is universally unique. So we hash that data and we pass that as the argument. And the constraint here is that if a cell with type ID code, like here, appears only in the output, so there's no complementary cell in the input that also has type ID, then the hash of the first input, i.e. the hash of the transaction hash and the index of the first input, must equal the hash that's passed in as an argument here, okay? So that's basically creation of a cell that uses type ID. So the question is, what if I tried to create this again? Now, if I tried to create this output again, but with different data, for example, but I try to reuse it, I have to, or sorry, I try to create a new output with the same code hash in args. I have to include that value that is the hash of the previous output. And the type ID code will enforce that, will look through the inputs and enforce that the first input has to equal to this. But since you can only spend an input once, you cannot find it. And you cannot find the input that has this particular hash. And so by default, you can only create that arg once validly with type ID. And then, of course, if you want to use a cell with type ID, say you want to consume, you want to use it as an input, consume it, and use it as an output. Like I said, when you use a cell as input, you destroy it basically from the developer perspective, and then you can create a new cell as output. So the type ID logic also enforces that if a type ID does appear in output, if a type ID cell appears in output, and the arg passed to the type ID does not match an input in the does not match the hash of an input, then that means that you're creating a new type ID cell, but you're not you're not creating a new type ID. It implies that you're using a type ID as both input and output. So it's going to enforce that exactly one cell in the input has the same type ID as the exactly one cell in the output with that type ID. And the reverse is also true. So that's essentially how type ID works. And there is code for this in here as well called type ID. So type ID is a system script, but very expensive to run, and you can just run it yourself with some sort of customly created script, and that is what this does here. And I'm just showing you that so that you see that script does exist in this repo for your reference, and there's some nice commenting here to explain how it works. Okay. And that's all I have for today. So we went over how to add transfer to UDT, how to design maybe a different type of monetary policy, as well as how to make use of type ID to make our tokens more secure. And then you can, for another of the concepts, I think that anyone who wants to go through the actual project that I've been using in parallel with this presentation can do so and understand everything in there if you don't already. So with that, are there any questions? Oh, I do see. Okay. All right. So it doesn't look there are more questions then. But so I guess check out the project, and if you are participating in the internal hackathon, good luck. Ping me if you have any questions later on Telegram. But other than that, thanks everyone. All right. Bye.